Hey guys, we are back together and we are continuing to work on our transformations. Third one up for us is rotations. So let's dig into rotations here. So a rotation is a transformation where the figure is turned about a fixed point. So we're spinning it around. Um, Now, what we're working on is the center of the rotation being the origin of the graph. Rather than the center of the shape or the figure, we're considering the entire coordinate plane to be our figure, and we are rotating it around the origin. So one thing I always try to tell my students for visualizing, graph the original, put your pencil point on the origin of the graph paper, on the origin, and turn the entire piece of paper under your pencil. That's what we're doing. We're not just spinning the shape. In today's work, we're not rotating it around any random point. We are very specifically rotating the entire coordinate plane. Okay. Now, this video, as I've given you guys in the past, this is a video by Mashup Math on YouTube, and it is excellent in the sense um, how they animate the rotation so that you can really visualize it in a way that you can't do on a static screen. So props to them. And again, there's many others. There's other good ones. This is just one that I thought was fairly simple to understand, very straightforward in their explanation, and simple animation so that you can see what is happening in a rotation. And I definitely suggest folks go watch that video again or for the first time as needed, whatever the case might be. Now they show you all six rotations, six basic rotations, clockwise and counterclockwise, 90 degrees, 180 degrees, 270 degrees. So in chunks of 90. Of course, 360 would put us back to the original figure. So this figure, this is a screenshot. Well, it's from a geometry textbook, and it shows us the basic rules of rotation. Now, again, in the video, they showed you six different rotations, and I'm going to show you those six the way it fits here. First of all, we've got clockwise and counterclockwise. So positive degree is counterclockwise. So there's a few things that we have to understand. Positive rotation is counterclockwise, opposite the clock. Counterclockwise. It's a big word. So counterclockwise. So that's why in this image, they're showing you, for example, a positive 90 degrees takes us from our, rotates counterclockwise for our image. And they're giving us the rule. For a rotation of 90 degrees, take the A and the B, which is really the X and the Y, swap them, and then change the B value to a negative. So change the Y value to a negative. Again, we're typically using X's and Y's, but this is a textbook showing it to us. And what they're doing is saying move the Y up front, but change its sign, multiply by -1, and put the X value to the back. Now, that's no big deal. That is what we're being asked to do. So you can see the three rotations there, a positive 90, a positive 180, and a positive 270. Now that 180 should look kind of familiar. It's similar to something that we've done in the past. But again, every transformation has its own rule, and you want to make sure that you're following the correct rule. So they gave us positive 90, positive 180, and positive 270 in the textbook. Well, what happens when we have a negative rotation? And this is what's really important to understand. A negative rotation is clockwise, but a negative 90 is the same as a positive 270. And I'll show you exactly what I mean here. Let's consider our axes. And let's take the point A. Well, a positive rotation would bring us here. But that is the exact same thing as a negative rotation 3/4 of the way around. So again, we want to clarify here, a positive 90-degree rotation is the same as a negative 270-degree rotation. So do we really need two different rules for the same thing? Well, maybe. It depends on the individual. You could have 6 rules in front of you and pick the right one, or you could have 3 rules and understand 90 degrees clockwise, counterclockwise is the same as 270 clockwise. 180 clockwise is the same as 180 counterclockwise. They're the same things. So you have to determine as an individual what's better for you. Write out all 6 rules, or the 3 basic rules and understand that clockwise and counterclockwise work together. All right? And I put that together here on this slide for you as just a summary. But you're going to need those rules from the previous slide or from the video. Let's jump right into an example. And we're going to perform this composition. So the first thing we're going to do is graph the original triangle with the given points. So I'm going to do step 1 right here in blue, points J, K, and L. So J is at 2, 3. K is at 1, -1. And L is at -1, 0. So there's our first triangle. We're going to do our second step. I'm going to put my second step in green. And I'm just going to do the work right here. It says take your original point, subtract 4 from the x, subtract 4 from the y. So that means J prime. We've been working on our translations. So 2 minus 4 is -2. 3 minus 4 is -1. The entire triangle is sliding 4 to the left and 4 down. So I'm just going to find my K prime, 1 minus 4, and -1 minus 4. And my L prime. So -1 minus 4 and 0 minus 4. So now I can plot my points. J prime is -2, -1. K prime is -3, -5. And L prime is -5, -4. And as expected, we have congruent triangles. The second one is just slid left and down. Well, now we have to do our final step of the composition, which says a rotation of positive 270. So I'm just going to go to my notes, and I'm going to get the rule. For a positive 270, it says bring the y value up front, push the x to the back, but change its sign. All right. So we're just following the rule. Now again, a positive 270 is the same as a negative 90. So if it said rotate negative 90, I would go to my 270 rule and write it down so that I can perform it. We just have to understand that connection. All right, so let's see what we have here. J double prime. The y value comes up front. The x value goes to the back, and then change the sign. Multiply by negative 1. K double prime. Again, my y value comes to the front. My x value goes to the back times negative 1. L prime. Y value to the front. X value to the back times negative 1. And now we're going to plot my points. Negative 1, 2 is J double prime. K double prime is at negative 5, 3. And L double prime is at negative 4, 5. And you can see that from the green to the red, from step 2 to step 3, it was definitely rotated. And you can achieve the same result by putting your pencil point on the origin and turning your paper either counterclockwise 3/4 of the way, 270 degrees, or clockwise 1/4 of a turn, meaning 90 degrees in the negative 90, meaning in the clockwise direction. And you can visualize where this triangle is going to end up. Again, we have our rules, we can simply follow them. Now, the other thing that we talk about in this section of rotation is the idea of rotational symmetry. Rotational symmetry means how many times can we turn a figure around its center. So we're not on the coordinate plane now. We're just saying how many times can we turn this figure around its center and it land back on itself. Now, there's another way to say that. How many lines of symmetry does the figure have? So the way we get rotational symmetry, and we can certainly make a little formula out of this. There's 360 degrees in a circle, in a full rotation, and we're going to divide by the number of lines of symmetry. And that's going to tell us how many degrees of rotational symmetry we have. So let's look at an example here. The rectangle, the answer is 180 degrees. Well, how many lines of symmetry does it have? We have one line of symmetry, and we have two lines of symmetry. So 360 divided by 2 equals 180 degrees of rotational symmetry. Meaning every 180 degrees, the figure lands right back on itself. If we look at a square, we have 1 and 2, but then we've got the diagonal lines of symmetry, 1 and 2. So 4 lines of symmetry. 360 divided by 4 tells us 90. So every 90 degrees, we have rotational symmetry. Now, typically we identify rotational symmetry between 90 and 180. So we could say 90 and 180, and then it would keep going. Or we can say every 90 degrees. An equilateral triangle has 3 lines of symmetry, so 360 divided by 120. So let's look at just a couple other quick examples. We want to determine if the figure has rotational symmetry and state the degrees. Well, again, we're looking for how many lines of symmetry there are. So there's definitely symmetry there. In fact, to all these outward points, these convex points, we have symmetry. So that's already 4. Now we also have lines of symmetry to these concave points. So we have 8 lines of symmetry. So 360 divided by 8 is 45 degrees. So we have rotational symmetry every 45 degrees. If we look at our last figure here, we certainly have a line of symmetry there. And we have a second line of symmetry. So as we said, 360 divided by 2. And we have rotational symmetry every 180 degrees. Meaning I can rotate it 180 degrees and it would look identical to its original. And those are our rotations. Again, to recap, positive degree rotation is counterclockwise, negative is clockwise. And then we have our standard rotations of 90, 180, and 270 degrees. So you have to know which direction you're going and how far. And again, positive 90 and negative 270 are the same thing. Positive 180, negative 280, same result. And of course, positive 270 and a negative 90 produce the same result. All right, let's do some practice with rotations, and we will pick up next time.